Dr. Hadi Madani is an assistant professor in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. He earned his PhD in civil engineering and his MS in electrical engineering from the University of Southern California in 2012. Prior to joining UIUC, he was a postdoctoral research associate in the Department of Aerospace and Mechanical Engineering at USC in 2012 through 2013, and in the Scientific Computing and Imaging Institute at the University of Utah in 2013 through 2014. He's a recipient of the NSF Career Award to study fast computational models for energy transportation systems. He's also the recipient of the Student Paper Award in the Probabilistic Methods at the ASCE Engineering Mechanics Institute Conference in 2012. His research interests are uncertainty quantification, scientific machine learning, and decision-making under uncertainty. Please join me in welcoming Professor Hadi Madani.
Good morning, everyone, and thanks, Calvin, for the presentation. So the topic of the presentation today is the integrated truck drone freight delivery system that we are studying, and we're presenting a particular case study trying to quantify the benefits and costs associated with an actual implementation of an integrated system. This is a work carried out by a number of groups. As you can see, the number of authors and researchers on this slide. So most of the groups are from University of Illinois, and Professor Ozer is from the Arizona State University. So there are groups working on the pavement and facility side of the project, and groups working on the operations side of the project. So I try to do a good job presenting the research work done by different groups, even though I'm not an expert in pavement design, but I'll try to do a good job. If you have specific questions and details, please do ask. I'll try to answer them. And also, there are PhD students from those groups in the audience, and if needed, they can provide more details about the implementation. All right, so what is truck platooning? Truck platoon is a group of trucks that can travel very closely to each other, almost like a train. So the headway is going to be smaller, and then that has various advantages. If you can have a platoon of trucks traveling together, then it will lead to more regularized traffic, and it can improve the traffic flow because there's going to be less braking and accelerating involved, and the congestion is going to be, as a result, reduced because of the background traffic doesn't have to pass trucks, so all the trucks are platooned together. Another advantage, which is arguably the more important advantage, is the lower fuel consumption and emission that is associated with the reduced drag force that is applied on the platoon compared to the case where trucks are individually traveling over a road. So with the new and enabling technologies that we have in autonomous and connected transportation, platooning is becoming more and more doable. And you'll see this more and more prevalent. All right, so here's a big overview of the research interest that we've had in this project so far. As I said, this is a holistic look at this integrated platoon, truck, and drone delivery system. On the top, we're looking at the impact or the benefits or costs associated with the facility side of it. What's the pavement performance if you have an integrated system. We're also looking at a new technology that can be embedded into the roadways in order to provide more opportunities for precise positioning of platoons. So that is a V2I communication system that I'll present momentarily. Then at the bottom, we have the operational aspects of it. So if you have a platoon of trucks, how do you quantify the fuel saving due to the reduced drag force, which is a function of the speed of the platoon and also the wind direction and wind speed. And eventually, how can you have an optimization and control framework that can optimize the spacing of the platoon and the lateral positioning given the particular wind characteristics that you face during the trip. And then the last part is the last mile drone delivery. So the idea here is that you have a platoon of trucks that are delivering freight, and when you get to the destination, so in this case we are starting from somewhere in the south of Chicago, and then there is almost 100-mile distance that they travel by the time that they go to a city, Rantoul, or a village of Rantoul in central Illinois, and there are the last mile deliveries. So these are parcels and packages in a hypothetical scenario that the drones are gonna fly to the trucks, grab the parcels and deliver it to the addresses in that area. So we want to also optimize that process and calculate the costs associated with that integrated system. So the cost per parcel, we want to quantify that in order to quantify the total advantage that we get from the system. So these are the four components of this integrated connected platoon or platoon truck and drone freight delivery system. All right, so the objectives that we have in this work and the results that we're presenting are in 5 different categories. The first one is on the planning and design of the facility that is suitable for this integrated system. So the first one is creating an embedded passive sensing material system in the platoonable section and study the cost and safety benefit that it actually it's associated with it for controlling the lateral position of freight trucks. The other one is to quantify the damage that the channelized traffic flow, which is the truck flow, that are moving in platoons. So the flow is more channelized. So that channelized pattern is gonna cause more damage to the pavement. So we want to quantify the pavement damage as a result of that, and also study ways to reduce that damage, and study how that pavement damage changes with respect to the spacing between trucks, the lateral positioning of the truck, and eventually the number of trucks that you have in the platoon. There are operational implementations of it, implications of it. So the third item is the aerodynamics aspects of it. So as I said, the main advantage of truck platooning is that it reduces the drag force, and as a result, the fuel consumption is going to drop. So we want to study how different spacing between trucks and different directions and characteristics of wind is going to impact that drag force, and how can we quantify that fuel saving for a case study or the scenario that we're considering between Chicago and Rantoul. Also, the last mile drone delivery, study how effective that system is for last mile delivery versus a manned service. So where you have trucks, and then there is the last mile is just delivering in vans, for example, the regular UPS or Amazon kind of delivery. And once you've set up these 4 systems, we also do the life cycle cost analysis in order to calculate over a long period of time how much is going to be the cost of the system, what's the excessive fuel consumption associated with different options that we have. All right, so as I said, the goal is to compare the costs and benefits of an autonomous and connected or a platoon system together with a drone system with the traditional truck freight delivery. The path that we're considering for this case study is shown here. So the origin and destination is almost 100 miles apart, and the main goal that we have here is to provide the agency with a complete picture of the implications of the policies that they're considering on truck drone freight delivery. All right, so I'll begin with the first task, or first goal, which is designing an embedded system for the roadways to improve the lateral positioning of trucks. So this is a V2-1 sensing for lane keeping. So it's a very important thing for safety. 50% of fatal accidents are linked to lane departures. So the idea that we are pursuing here is to place continuous electromagnetic signature near the middle of the lanes. All right, so there is that field. So it channelizes the Earth's magnetic field, and if you then have a magnetometer installed on the vehicle, and there are deviations from the center of the lane, then those magnetometers can capture that. So we channelize the electromagnetic field on the roadway, and then deviations can be detected. All right, so Professor Reisler at the University of Illinois and their students actually ran actual tests to study the effectiveness of the system. So there are lab testing. They consider different configurations of the dosage of the electromagnetic material and the shape of the specimen, the size and geometry, and try to see what are the implications of different choices. So the field testing is shown here. So this is the vehicle that is equipped with this magnetometer. There are also 2 cameras on side mirrors. These are installed to establish the ground truth. So what's the actual lateral positioning in the lane? And there is also a camera on the center of the vehicle that is used to establish an alternative way of doing the lane departure warning, mainly based on motion that is captured by that camera, and compare it with the errors and the effectiveness of capturing the lane departure using the magnetometer. The results, which is documented in the paper, showed that there is significant improvement, especially in snow conditions, where visibility is reduced and the camera may not capture the actual lines on the road and the location of the lane. Especially in those conditions, this electromagnetic field can be very effective. And it could also complement existing ADAS, especially for adverse conditions. The second research goal is to study what's the damage on the pavement due to the channelized traffic. So the first scenario is that you have a platoon of trucks, and they always follow the same path on the pavement. And so we have very precise positioning system, autonomous driving, and they will always keep their center position. The problem with this is that it will be more damaging because you're always applying the load on the same location in the pavement and in the lane. So platooning, if implemented in this way, is going to be more damaging compared to traditional traffic with more wonder. So the second scenario is that you have distributed traffic. So this could be either having platoons that are traveling over different lines within a lane. So you intentionally create some deviations from the center in order to distribute the load that is applied on the pavement. So each platoon follows a specific path. The path is selected and communicated to platoon with a centralized optimization policy. And then here, as you can imagine, especially if you're adding some lateral positioning within the platoon between different trucks, the fuel consumption may not be as low as a completely lined up set of trucks. But then there is a balance that between that, the fuel saving, and the damage that you consider on the pavement. And there are papers that we studied the trade-off between these two. All right, so here's a more detailed look at what the problem is. So if you consider this is the area, this is a cross-section of the pavement, this is the tire location, and the applied or expected strain is going to look like this. So if you slightly deviate each passing of the vehicles, that applied strain is going to be shifted. All right, the third objective, which was the truck aerodynamics and the fuel saving. So what we wanted to do in this case is to say, okay, you have a platoon of 3 trucks. There's a specific spacing between them, and there is a different load direction, wind direction and wind speed that is applied on the platoon. And in order to calculate the drag force for each of those configurations, you have to run a CFD, and that is a time-consuming problem to solve. So our goal was to create a surrogate model, which is an approximate model that can be trained on a number of training configurations or on a number of available configurations with the available CFD results that can then be used for unseen configurations. So we have considered a number of models that can be trained on a number of samples that you get from your CFD simulations. And then we tested them on unseen configurations. And as you can see, the neural network model, for instance, is doing a very good job in the prediction of the drag force. Okay, and this is the comparison between the CFD result and the generalized additive model that we have here, which is also very accurate. All right, so we studied this both for the purpose of this work in order to calculate the total saving between Chicago and Rantoul, because wind direction is different, wind speed is different, and we wanted to consider different spacing between trucks. So we didn't want to always run a CFD simulation if wind direction changes slightly. So we just made use of these surrogate models. This surrogate model can also be used for real-time control of the spacing between trucks. So for instance, if the wind direction changes, if the wind speed changes, and there is particular damage patterns on the pavement, if you in real time you want to reconfigure the platoon, you can do that using these surrogate models instead of having to wait for the CFD results to be available. And finally, the fourth component of this research, which is the last mile drone delivery. The main task is to design an optimal hybrid delivery system where trucks travel on existing roadways, and then when it gets close to the destination in the area, the drones simultaneously make the last mile delivery. So in order to optimize the system, since this is a difficult problem to solve, the Professor Ouyang's group studied how to use physics-informed neural networks in order to optimize that process and calculate the cost. So the inputs are different demand density, the truck speed, and the service range. And then this neural network model predicts the cost and the trajectories and the traffic equilibrium for that last mile delivery. All right, so with that introduction into what the main goals are for each of those 4 components, we get to this particular case study, and we wanted to now implement this system for this actual scenario on a given day in March with an actual wind profile, an actual wind measurement, and try to see what's the cost and benefits associated with that. So the corridor spans from a south suburban area in Chicago to the rural area here in Rantoul. The distance is approximately 100 miles. The platoonability for the corridor is really high. Truck of class 9 was considered, and the number of trucks in a platoon was considered to be 3. There are various spacings that were considered. For the, in particular for the pavement, there are a number of spacings. For the life cycle assessment, cost analysis, a number of spacings was considered, but for the aerodynamics, continuous set of spacings was considered. All right, so we studied the V2I sensing for lane keeping for this area. So if you have 100 miles between Chicago and Rantoul, what are the costs associated with that? So the labor cost was assumed to be similar to that of conventional paving. So the steel fibers that was designed in this work, the dosage was 1% by volume because that was enough to be detected under both normal and adverse weather conditions. So and the cost of the steel fibers are $800 per mile. The paving concrete delivered is $1,800 per mile, and there is approximately $3 per square foot that is required to provide a 3 by 3 inches squared or 3 inch by 3 inch groove in the pavement, and that adds up to $4,000 per mile. So these are the total costs associated with the implementation of this V2I system. So the modification during an appropriate rehabilitation, the cost there is $260,000. The cutting of the current pavement in order to create a groove is $400,000. The traffic control for the work zone is $250K. The labor cost is $300K. So the total cost is $1.2 million, or it's per mile it is $12K. So that's the cost of upgrading this segment, creating or embedding this electromagnetic field on the pavement. All right, so the pavement, so let's see what's the impact on the pavement performance. So there are different scenarios that you can consider for the calculation of the impact on the pavement. So the first one is the human-driven truck flow. So this is essentially, there are some natural wonders that a human driver is going to induce. So if you consider this 0 point to be the center or the location of the tires when the truck is exactly centered in the lane. So this is the location of the tire. So there is always some, variability in or deviations from that actual location if it's human driving. The other extreme case is when every truck is a autonomous, precise positioning, and then there is no deviation. So there is a centered truck. There is zero deviation because it's controlled by a machine. So then the impact is going to be very much concentrated on that location of the tire, which is associated with a centered truck, centered in the lane. So now what happens if there is a mix? So if you have 50% of the truck flow operated by humans and then 50% autonomous or precise flow. So in this case, you would get a background uncertain or normal, almost like normally distributed impact on the pavement, and there are the actual positions that you get the for the truck. But here is the case that the trucks are shifted by 14 inches, right? So there is one set of trucks that are traveling here and one set of trucks that are traveling there. That's another scenario. Then the third scenario is where you have 100% autonomous trucks. So the positions that are communicated to the trucks is the position that they actually drive on the road. And here we communicate 3 different positions. One is centered, and then there are 2 deviations. And the impact is going to look like this. And we want to study what the implications are. So here, in this plot, so this is months, and this is the impact on IRI, which is a measure for the condition of the pavement. So you see that the fully autonomous truck that is distributed on the sublanes, which is the green dashed curve here, is going to be the most efficient way of running the truck flow on the pavement, because the lower the IRI, the better the pavement condition is. So the fully autonomous flow is going to result in the lowest distress. So, but what you can also see in this plot is that even if you have like 50% or 25% of the truck flow to be autonomous, or to be platooned and autonomous, that's going to be beneficial because there's going to be a lower impact on the traffic. On the pavement compared to a fully channelized truck flow. All right, so the next results that we have for this actual case study is the truck aerodynamics and the fuel consumption. So, the interstate between Chicago and Rantoul is I-57. We collected the wind data from wind station located in Rantoul and Kankakee, and the wind here is the wind speed that's collected together with the wind direction during that 24-hour period in I think the day in March. Using this actual wind profile, we calculated the drag force on the truck platoon, and that is coming from the trained surrogate model. So the figure that I'm showing here are showing the fuel saving, the percentage of fuel saving compared to individual truck flow versus the truck headway. So this is the spacing between the 3 trucks, and the spacing is the same. So the first and second truck has the same spacing as the second and third one. So here you see that the lead truck, the fuel space saving is not that much for the lead truck, but the middle truck and the trailing truck, which is the green and yellow curve, there are significant fuel saving. And this is the average fuel saving for the 3 trucks compared to a platooned scenario and the individual scenario. And as you see that here, the more closer the trucks get together on a platoon, the more fuel saving that you can see in terms of fuel consumption. So this is like almost 10% if it's very close together. And if you increase the headway, they almost get to a point that it's as if they're like traveling by themselves. So there is no platoon, right? So and then the fuel saving drops. All right, so this is the last mile drone delivery results. So in the optimization problem that you want to optimize the operation of the system, there are different configurations that are optimized. There are different costs and numbers and specific parameters that are considered in this study. All those things can be different, and still the same optimization framework can be used to optimize this operation. So here the cost of running or operating a truck and the cost of running a drone is given. The drone delivery is cheaper because it reduces the labor cost and it allows for longer delivery headway. So this is the a figure where we have shown the total cost associated with this operation. So there are different scenarios that we are considering on the truck side and then on the last mile delivery side. So the first one is when you have the truck delivery to be platooned or manned. So this is human driven trucks. Then on the last mile side, you have manned delivery using vans or trucks, or the truck drone hybrid system. So these are the 4 different cases. On the y-axis, you have the delivery cost, which is per parcel. So this is assuming that you have you have a number of parcels, and then how much cost associated with that delivery. All right, so then there are the costs here. There are the truck fuel, the truck handling, drone energy, and all those parameters that are included in the optimization problem. And as you can see, this option of platoon plus truck drone last mile delivery results in the lowest overall cost that you can see here. So the average cost is reduced from $1.58 to $0.97, almost $1 per parcel. This is 38% reduction. All right, so we also studied over a 20-year period what's the life cycle cost assessment of this system. So on the left, we are looking at the excessive fuel consumption due to the IRI. So this is the pavement condition. If the pavement condition is different, the fuel consumption is going to be different. So if you have poorer condition in your pavement, the fuel consumption is going to go up. I wanted to study that effect considering different scenarios. So these are the different headways that are considered. So 18, 65, and 20, because the different headway is going to result in different damages on the pavement. So you have for each one of those headway scenarios, you have 5 different cases, which is fully human driven, fully channelized, and then 25%, 50%, and 100% mix of human and platoon truck, but with some deviations that you induce on the lateral position. The y-axis is the excessive fuel consumption. As I said, this left block of bars is related to the IRI-based cost or fuel consumption. And as you can see, this mixed traffic, mix of truck and background traffic, is going to result in lower excessive fuel consumption. On the right-hand side, we are showing the excessive fuel consumption because of the fuel consumption in trucks. So this is due to drag and also the fuel consumption that we are considering. So here, if you have fully channelized, you get this. So there are 2 bars that are shown on top of each other in this figure. So the one on the front, these are the fuel consumption. The the one in the background is the fuel saving. So for example, in these cases, fuel saving that you get from platooning is more than the fuel consumption. So it actually offsets the excessive fuel consumption. The saving that you get from the platoon configuration offsets the excessive fuel consumption for cases that you have platoons. And then you see here, if you for all these distributed cases, you have the fuel saving that is larger, and in like worst case scenario, they're almost the same as the excessive fuel consumption. All right, so let's get to the conclusion. So overall, we concluded that the integrated connected truck drone delivery hybrid system was beneficial over conventional delivery operations. So we saw that distributing truck platoons may reduce the user cost for both platoon trucks and passenger vehicles by up to 15 and 11%, depending on the truck headway. So we also showed a methodology that, or technology that can be used for the accurate positioning of vehicles and trucks that is going to be robust and resilient, especially in adverse weather conditions where poor visibility is gonna affect the vision-based detection systems. The cost was around $12,000 per mile. And we saw that the lower the spacing between truck, the better. It's gonna lead to higher fuel saving, and also for pavement performance. We showed you a neural network and other types of surrogate models that can be used to replace a full-scale computational fluid dynamics simulation that can be used to predict the drag force under different wind conditions. So the average fuel consumption reduction ratio could be due to the platoon, then reduction of the drag force could be up to 10% for the whole platoon of trucks when the spacing is as small as 18 feet. And this was what we calculated considering various wind condition between that the origin and destination. The hybrid system of truck and drones incurs lower operational costs in terms of per parcel values, up to 70%. Using drones for simultaneous delivery, the service time could also be drastically shortened. With that, I conclude my presentation and would be happy to take questions. Yes.
Yeah, thank you for the insightful and comprehensive analysis.
Thank you.
And I had two questions.
Sure.
One is a clarification. So for the headways between trucks, it does matter the size of the headway. There is a difference between that and the damage you incur on the pavement. Is that correct?
Yes. So there is a, yeah.
Mm-hmm. So it's not just the weight, but also there's some frequency.
Yes, there is actually also a particular behavior of the pavement, which is the resting period. That is something that our facility and pavement group is studying. Do you want to add more?
So yeah, to answer your question, yes, it does have impact spacing. And so what we did is, there is a group in Arizona, Professor was there, he conducted experiments about what would be the influence. And he found something like counterintuitive, that is, as you increase the spacing, you result in more permanent information, which is very counterintuitive. And the current hypothesis for that is something called the hardening relaxation mechanism. So I'd be happy to discuss with you more on that if you are interested.
Definitely. And I have a second question.
Sure.
So you've analyzed the different distributions of vehicles laterally in the lane.
Yes.
Are there studies on how the vehicles are distributed naturally?
The impact on the pavement is mainly due to trucks, right? So the passenger, like the sedans and SUVs, they don't damage the pavement that much, right? So if you mean deviations, the natural or actual deviations that vehicles have, so probably you should look at the deviations that trucks usually have. I don't think there is any study or.
So just to add again one more point to that. So there are two things, right? One possibility is there is no platooning, so it's just conventional driving operations. So it follows a normal distribution because humans have their, idea of saying that. There is another thing is if we have platoons, so you really can control the lateral position. So you want to engineer it in such a way that within the lane, so if you take the lane with just 12 feet and your truck is 8 feet, so that is the 2 feet you can jiggle around. So the idea is you go a little bit towards the center of the lane for one set of platoons, for another set you go a little away. So the one that you see with the sharp, distribution, that is something we wanted to do for platoon. It's not something you observe on the field, but it's something what we propose that platoon should follow such kind of distribution. That answers your question.
And I was just wondering, another follow-up question. In case you have a lot of these trucks in a platoon, would the ideal distribution be uniform?
The lot of trucks within a platoon?
Yeah.
It won't, right? Like, so the idea is, let's say there is 100 platoons. And what we engineer, like, let's say the 3 lanes, 3 sub-lanes within the lane, 3 positions. So when I say 100 platoons, the 33 platoons will go on this sub-lane. So whatever number of trucks is there within that platoon would go channelized. So within the platoon, all trucks are channelized, if that's what your question is on. However, between 2 platoons, that's where you control your lateral position.
Yeah. Let us talk more. Yeah.
But
I want to follow up.
Yeah, but I if I may add to that, so there is a central limit theorem that essentially says that the average of a large population of samples from any distribution is distributed according to normal distribution. So even though there is no actual observation on how the deviations look like in terms of the wanders or the deviations from the center, you could say that normal distribution is a good approximation. But back to your point, on what's the optimal. So I would say, assuming that you have uniformly put in the resource, which is the pavement strength and everything is uniformly put on the lane, right, across the lane, then a uniform distribution of load would be theoretically the best option to achieve, right? So now, in terms of implementation, whether there is practical advantages of like just saying 4 different channels or 5 different channels versus infinitely many possibilities that lead to a uniform distribution, that's a practical implementation choice.
And just to add a point to that, so what we observed is we did see like different sublanes, like we here you see 3, like left, right, and center. We had like 5, 7, but the advantage really decreases once you go beyond this point. And we chose this sublane with us 2 inches because we are again limited by practical constraints. If you listen to the earlier part where we had a magnetometer and the accuracy of that lateral positioning is around 2 inches. So we really cannot have a significant, first we don't have much advantage if we increase the number of sublanes, and 2, it's again the practical issues.
So there is naturally some deviation, even though you want the trucks to be exactly in this one. Since the actual technology has some errors, there's going to be a slight perturbation, so that could help. Yeah. Yes. In the back.
Could you speak a little bit about the decision of the electromagnetic center line, and maybe some considerations as far as just relying on the markings themselves, because the road needs to be marked rather than adding the additional cost of the magnetic strip in the center. I wonder if there could be some type of programming that could be done to say like 3 different settings for a truck to say center line closer to the or center of the lane closer to the center line, closer to the edge line, as far as like programming the ADAS technology relying on the markings themselves.
So are you saying that instead of the center you could place the sensor or the field somewhere else on the lane, or just like rely on vision based?
Rely on vision based.
Okay, so as I said, the full reliance on vision based, which is actually something that's a lot of autonomous driving, even Tesla is like doing away from LiDAR systems, and so it's because of the advances in vision based technology. Is very reliable, but assuming that the weather condition is fine, right?
Mm.
If there is a snow and the snow is not cleared in time, then you lose that, right? So the idea here is to have a more resilient, more robust system.
Thanks.
Yes.
Hi, thanks. I was just wondering, so with the magnetic line based versus the vision based, is it really only for sort of having the platooning in like the winter conditions, or would there also be an improvement during like normal conditions as well?
I don't exactly remember off the top of my head. Do you remember about the results, the error that you get from the two systems? Yeah.
So again, there are two false advantages. The first, like I would really suggest, I wish my colleague was here to explain in detail. If you just have vision-based system, I understand you can still have some kind of lateral positioning, but that goes off in snow conditions, right? Like he tested for different snow conditions. In Illinois, we have plenty of snow, so like for different snow conditions, the normal camera system didn't seem to work. However, having said that, even during those tough snow conditions, having a magnetometer or like a magnetometer on your vehicle and like the electromagnetic properties on pavement, it helped us position accurately with the margin of like plus or minus 1 inch. So that's the 2 inch. And coming back to the normal conditions, yes, it did improve, and the vision-based system itself was accurate. But compared to that, this was even better. I don't remember the numbers in the top of my head. I would really suggest you to go to the report.
But there is another consideration, and that is adding this technology to vehicles, right? So this is going beyond truck platoons and truck systems. So just imagine if you have a car. If you want to equip it with vision-based system, so you have to install cameras, right? And then you have to install a vision-based software that runs that. This technology, the detection of deviation from the lane, that doesn't take a lot of computational power and is very specialized software, right? So if you have an old car that doesn't have any safety feature, you can just install, assuming that the road is equipped with this magnetic field, then you can just install a magnetometer on the front of the vehicle, and then have it give you a warning system right away, right? So in a way, you like outsource the cost to the facility, to the agency to make smart roads. Then the additional cost that the drivers need to equip their vehicles towards better safety features or safety standards. That's a reduced cost. So there is a balance there, right?
Sure. So another follow-up question for the magnetic field approach. Are there any like extra safety or extra maintenance issues that you have to worry about once you install this thing in the road, or is it pretty reliable?
Yeah. So as far as I remember, there is an overlay of pavement on the fibers, So it doesn't need any maintenance. So even if it is, for example, off, I think, I don't know if they have studied this, but so if there is damage to the pavement, and the damage is like deep to impact the fiber, that's going to be the only reason you may want to maintain or fix it. But I mean, normally you would want to fix the pavement because of the safety concerns when there's a pothole or there is a major problem with the pavement. So there is no maintenance, like additional maintenance routine that you need to run for these kind of systems. So it's a passive system. It's not like an active system that you need to like run on a power, and then it has to be kept on and it has to be turned on, and it's not like, it's a passive sensing.
So it's not powered then, or?
No.
Okay, so it's just the magnet passing over the cable.
It's basically a small prism which has steel fibers in it. Because the current pavement does not have any electromagnetic properties, all your things that is happening is on your vehicle. That is the magnetometer. So it really, let's say your vehicle is exactly on the top of it. The sensor over there will read the maximum because there are steel fibers beneath it. So the infrastructure in the road itself is just simply steel fibers in a prism, and it's laid on the pavement. And one more, one of the issues that they are trying to address is, so what happens if there is a PCC pavement and there are rebars? So because steel again has properties, right? So that's something they are studying right now. But just if you take an asphalt concrete pavement, this infrastructure itself does not have any sort of power requirements or anything. It's just plain prism with steel fibers.
I was actually wondering one more thing. You use this word platoonability. Yeah, I was just wondering if you could define like platoonability. Do you just mean like how long you can have the platoons, or?
Yes, so if it's a corridor and then there are not like major intersections with other freeways, and then so it's a rather long stretch of corridor, right?
Again, there is a study just to determine, we define something called platoonability index. So for, let's say, if you're traveling closer to Chicago and interstate, it doesn't matter because the exits are going to come for every 1 mile. So there's not really a chance of trucks forming a platoon there. So based on the traffic conditions and how frequent your exit or the ramps are, so there was an index that was developed to classify the sections if this platoonability level is high. That means like most of the rural sections in Illinois, interstate sections are platoonable throughout the day and night. So when we say platoonability, we mean how much efficient you can platoon, at least for 15 minutes, that's the definition. At least for 15 minutes, if the trucks were able to platoon without any interruptions, we call it as a highly platoonable sections.
There's also studies into whether it's feasible to dedicate a lane to platoons, either add a lane. I mean, this is assuming that in future you will see more and more platoons, and maybe it's worthwhile both from the efficiency and also safety aspects to have a dedicated lane, add a lane to a road just for the platoon trucks. So that's another thing that's studied.
Okay.
All right, thank you so much for all the very interesting questions, and I hope you enjoy the rest of the event.
Thank you, Professor Madani.